Okay, students, good morning. Welcome back for today's session. Okay. And hope the PowerPoint is visible to all of you. So we are discussing about materials that have been used for 3D printing. And yes. So far we were discussing about variety of materials that are used in engineering, in particular in 3D printing, that is metals, polymers, ceramics, composites. And materials are always process specific, as we have already seen. Okay. Today we have discussed about FPM already, and FPM biostration. This is what we have discussed last time. And within this SLM materials, then we'll be coming for SLS and SLM, which is on powder forms. The fine grains, usually the grain size of the grains will be 10 to 45 microns. Okay, microns. Okay. So this is where we have stopped last class. Okay. So today we'll be discussing about one more that is the most advanced material which is used for SLS, that is self-less sintering, is ceramics. Okay. So the ceramics is nothing but your Al2O3, aluminum oxide. It is a mixed powder. It will be used in form of powder form, as you know, that is used for the SLS. So normally, the steel will be having the melting point somewhere around 1000 plus or minus 200 degrees Celsius, depending upon the aluminum alloys that is having. Okay. But this alumina, look at here, this alumina has a melting point of about 2000 degrees Celsius. Okay. So this is one of the very hardest material which you can see. It is actually an oxide. Okay, so this material is also used as an raw material for SLS, that is selective laser sintering. Okay, so since this is having a very high temperature, it is very difficult to bond this. Okay, using the sintering process. So what they will be using is they will be using a secondary component like ammonium phosphate or boron oxide, which will be having a low melting points. Okay, the melting points will be around 190 degrees Celsius or 460 degrees Celsius respectively. So they will be used as a binders. So we will be using the combination of mixed powder combination of alumina and the secondary compounds. Okay. So when you are increasing the temperature for about 400 degrees Celsius, when you are using this boron oxide as an binder material, for sure this binder material will melt and it will be responsible for the bonding of the aluminum oxide powders. Okay, so by this way we will be using the ceramics. As I already told you, when you are going for polymers, there is no necessarily all the polymers will be having a very low melting point when compared to the metals and ceramics. Okay, so there you not be needing a separate binding agent. But when you're coming for the ceramics and the metal powders, if you're using them as an raw material for the selective laser sintering, you need a third party binders. Okay, so that binders will be sometimes can be of polymers or sometimes can be of the same metals, which is having a relatively low melting points. Okay, so when you're using this alumina as a powder, you can have a reasonable dimensional accuracy, yes, and a part definition. Okay, so usually ceramics, that is what ceramics having generally high melting points. Okay, so it is exceedingly difficult, impractical for local densification. So in your local densification is nothing but you can't ensure a uniform densification throughout the component which is getting printed. Okay, that is why you'll be going for a coating or mixing of other materials of low melting point, softening points, acting as binders or in the matrix powder itself. So if you are going for binders, they'll be having you can go for polymers like this. The next point you can see binder can be either organic polymer or inorganic metal-based low melting materials, and of course glasses can also be used. If at all if you're using alumina, you can also go for glasses. Okay. But the two major concerns in SLS of ceramics are the high shrinkage and high porosity remaining in the final parts. So this is one of the very much major concern when you're going for SLS of ceramics. Okay, so if you are going for SLS of going for ceramics, for sure you need to go for a secondary operation in order to close the shrinkages or in order to withstand with the porosities also. Okay. So this, apart from this concerns, they are also increasingly used in biomedical applications, particularly in fabrication of customized, complex, and high cellular biocompatible scaffolds. So the scaffolds is the one which is already told you, which is used for tissue engineering. Okay. So this scaffolds will be acting like a container to which will be holding the living cells. The living cells can grow inside. Okay. So that type of application is very much suited for the ceramic products that have been manufactured using selective laser sintering process. Okay, so these are the SLS materials we already seen so far. There is nylon, which will be of two grades, PA12 and PA1111. So this nylon can also be combined with other particles which will be acting like composites. There is aluminum filled, glass filled, carbon fiber filled, and also the one of the most latest invention is the thermoplastic urethane powder, which will be using like an elastomers. It have a good elasticity, okay? And the ceramics. So these are the various materials that are used for selective laser sintering process. Okay? So this is a guide which has been given by a company for selection of the SLS material. Okay. So this right side, left side, you can see the material properties which are having their own indications, and right side you can go for the material type, which is the color-based material type. The material type is color legends, and the material color is this type. Okay. So if you want to have a say nylon 1-2, okay, so go for this. These blue colors are nylon 1. Okay. So within this, if you want this red, this color, this block is called as stiff and rigid. Okay, if you want a rigid one which withstands high temperature and you need it in a black or white color, you can go for Duroform HST. So by this way, you can select a material based upon the application that is required for your concern. Okay, so this is about your SLS materials. So now coming for SLM. Okay, so when you're coming to SLM, is nothing but already you know it is selective laser melting. Okay, so the selective laser melting has been attempted. We have discussed about the history of this. It has been attempted during 1990s. The first company to come up with this is the DTM Corp. Okay, so they were using the earlier materials like rapid steel, one of their own production. That is a thermoplastic binder coated carbon steel powder with copper as infiltrant. So they'll be using thermoplastic is nothing but we already know it is a polymer binder coated on the carbon steel powder. So the steel powders will be there upon which you will be coating the thermoplastic binder, and we'll be using copper as an infiltrant. Infiltrant is nothing but when your materials are getting bonded, there will be some gaps or pores. Okay, we'll be calling it as pores. Yeah. So the pores will be there inside. Okay, so when you're this getting bonded, these coppers will melt ahead of this steel powders, and they'll be occupying the gaps that are formed during the densification process. So that is an infiltrant. Okay, so the parts produced using this rapid tool were debinded. That is, debinding is another process. This is a post process. Okay, then sintered and finally infiltrated with copper to produce final part with approximately 60% low copper steel and 40% copper. So this is the composition of the final part will be 60-40. 60 will be the steel powder and 40 will be the copper. Okay, so you use copper. I hope everybody know this. And this was again upgraded with this material was upgraded using the next version of this is Rapid Steel 2.0 that was introduced in 1998 by the same company DTM Corp. Okay, so it was a dry blend of stainless steel powder. So earlier it was a carbon steel powder. Now it is a stainless steel powder with the thermoplastic and thermoset organic binders with an average particle size of 33 micrometers. 33 microns. Okay, so the particle size was 33 microns. So look at how fine the powder particles are. Okay. So this Rapid Steel 2.0 produces functional tool parts, toolings and parts and mold inserts for injection molding. Okay. Right. So here instead of copper, you'll be using bronze as the infiltrant. Okay. So earlier we were using copper as an infiltrant, whereas here we'll be using is bronze as the infiltrant. So the final part will be having 50-50 composition, 50% steel and 50% bronze. Okay. So usually the rapid materials that have been done using rapid steel 2.0 was structurally more stable than the rapid steel materials. Okay, these were earlier stages, but now the latest one is here. Okay, so since it is about more than 2 decades in research for this SLM materials, there are a variety of materials being introduced by each and every company. Okay, there a company which is manufacturing an SLM machine will itself manufacture the materials used for those particular SLM machines. Okay, but they generally fall around 4 or 5 categories. That is aluminum based, iron based, nickel based, cobalt based, and titanium based. Okay, so all these will be powder materials with having a very fine powder structures of about 10 to 30 microns. Okay, the powder particles will be that much finer. Okay, so I am giving you a collection of materials that has been determined by this company, SLM Solution Groups. This is one of the leading company who manufactures SLM machines. Okay, so the name is different from company to company, but the composition will be remaining the same. Okay, so let us see about these materials one by one. It is a quite a lengthy thing, so please bear with me for today. Okay, I need to cover a lot of portions. So, so first is the aluminum based alloys. So aluminum based alloy means aluminum will be the maximum composition, along which you will be adding some other materials. Okay. So look at here the first material. This is aluminum, silicon, and magnesium. So this is a combination of aluminum, silica, and magnesium. Okay. So this has a very good corrosion resistance. Okay, where this material has a very good corrosion resistance, good electrical conductivity, high dynamic toughness. Okay, dynamic toughness is we can use for dynamic applications. Okay, wherein you will be having repeated loads. It can also withstand the dynamic properties. One of the properties is fatigueness. It can have a good fatigue life. Okay, and excellent thermal conductivity. So these are the material characteristics which you'll be finding for this material. So if you want a product which to have good corrosion resistance, good electrical conductivity, and good thermal conductivity, you have to choose this material as the raw material for producing that particular object. Okay, object or component. So usually this material is used for aerospace applications, automotive engineering, and heat exchangers. Heat exchangers. Okay, so this is aluminum, silicon, magnesium one. Another series of this is aluminum, silica 7 and magnesium 0.6. Okay, so here you can see the difference. Here silica is 10%, magnesium is very negligible. Whereas here is silicon is 7% and it is magnesium 0.6%. Okay, so they'll be just if you're varying the composition of these alloying materials, their property will change because aluminum will be having one property which you already know. Aluminum is very soft and lightweight. Okay, but it is not having higher strength. So if you're adding silica, it will be adding more strength. If you're adding magnesium, it will be increasing the thermal and electrical properties. So that way you can have the combination of required functionalities that can be tailor made into the materials that has been required. Okay, so here for this material, the metal carries a good electrical conductivity. Okay, so excellent processability. Processability is nothing but you can use this material without any extra work. Extra work here means we need to have some pre-processing and some post-processing that is not required. Whereas in this case of this. Okay, so of course it will be having good corrosion resistance and also it has a good tolerance against strain. tolerance against strain. Strain is nothing but when you are increasing the uh, particular component more than its limit. Okay, more than its limit. Okay, so for example, if you can stretch a material only to 10 mm, means if you are stretching the material more than 10 mm, 10 millimeter, it becomes a strain. Okay, so that strain will lead to, obviously the strain will lead to the failure of the material. Okay, so this is a tolerance, good tolerance and strain means even if you are increasing more than the limit, that is if you are increasing the stretching the material more than 10 mm, it can have a good resistance, it can have a good tolerance. Okay, it won't fail easily. Okay, of course it is having a good thermal conductivity. And applications, these are the applications which is the most common application which you can find. Okay, then another material is AlSi9Cu3. This is Cu3, not 0.6, not here, Cu3. Okay, so this is a metal cancer has a good, excellent processability. Yes, of course. So this will be had this both will be having the same or a similar kind of metal property, but is in order to increase the processability, you are adding copper into it. So look at here differences here. You are adding magnesium, you are adding copper into it. Okay, since you are having adding copper, this copper has a good electrical conductivity. Obviously, all of you know all the copper wires, all the wirings which are done in your electrical lines are having is the main thing is a copper. Okay, so since you are adding copper, it will be having good electrical conductivity, good temperature strength, high temperature strength, and thermal conductivity. Okay, so this is about our aluminum-based alloys. Means you are adding these other materials into aluminum in order to get the required characteristics. Okay. Next is nickel-based alloys. So nickel already you know this is an material. Okay, so with this there are more than 5 base alloys. I am giving only the main 3 alloys which are being used. Okay, and this HX is a nickel-based alloy with the high contents of chromium, molybdenum, iron. So obviously you could have come up with these terminologies in your chemistry. That is chromium, molybdenum, iron. Okay, so that is this nickel will be having the additional properties of chromium, molybdenum, iron. So this metal catalyst is high strength. Okay, it's a good ductility. Ductility is nothing but it can bend. Okay, good bending properties. Okay, then excellent oxidation resistance at high temperatures. Okay, excellent oxidation resistance. It won't get easily reacted with oxygen. Okay, so because formation of oxide is very much a big problem when you are going for high temperature applications. So you need a good oxidation resistance. So this will be giving it and high creep strength up to 850 degrees Celsius. Creep strength is nothing but high temperature. If you use in your high temperature applications, if you are applying load, that has to be withstanding it. That is what creep strength is. Okay, so obviously if you know not to explain this creep strength, if you're taking a metal, if you're beating it, it won't get deformed. Okay, if you're applying, if you're beating it with a hammer, it won't get deformed. But the same metal, if you're heating it to a red hot condition and if you're beating it again, it will deform. It means at high temperatures it is having a low strength. That is what the meaning is. Okay, so that is how this foundry, this forging process will happen. You can see some of the wherein you will be having some lengthy rod. Okay, இந்த அறுவல்லாம் பண்ணுவாங்க இல்லையா, so there they will be heating and beating it. They heating the metal to a red hot condition and they will be beating it. So since it is having exposed high temperature, it won't be having higher strength. That is the meaning here. So even at highest the degree, that is even at 850 degrees Celsius, it is having a good strength. That is the meaning of this. Okay. Next is iron 625. This is a material which is a precipitation hardenable nickel-based material alloyed with chromium, molybdenum, and niobium. So this is having niobium in it. Okay. So if it is having niobium, again it will be having the same properties of this, but will be having excellent corrosion resistance. So all these are mostly used for high temperature application. You can see here. Here it is a temperature application is about 850 degrees Celsius. Here also 850. Here also 850. The reason here is if you want to uh, 3D printer component which is being used at high temperature applications, you'll be going for these type of nickel based alloys. Okay, so similarly here in 939, you'll be having chromium, cobalt, titanium, tungsten, aluminum, tantalum, and niobium. So these are variety of applications where you can go for the combination of both these applications. So here it is having high mechanical properties, even 700 degrees Celsius, high corrosion resistance, even 850 degrees Celsius. Okay, so here you can see the application of this is a turbine parts. The turbine is nothing but the engine turbines. Okay, rocket engine turbines. They'll be having exposed to large or high temperature. That is, for in colloquial term, we can say it as aircraft engines. Engines which are there at the wings layer. So those engines will be having turbines in order to suck the air and supply it into the engine. Okay, jet engines. So those will be using, you'll be using going for this type of materials. Okay, so these materials are also used in your as a powder for your powder for SLM machines. Okay, next is titanium based alloy. So this is titanium based alloy. Here is the LE. You can the name here you can say it, titanium, aluminum, and vanadium. So these three combinations are put together to form a material here. Okay, so it will be having low density but good corrosion resistance and a high cycle of fatigue strength. So this is one of the main material characteristics which will be finding its application in aerospace and automotive. And of course it is, since you are using titanium, it is you can use it for medical applications as well. Okay, right. Next is TA15, which is an titanium alloy with additives of aluminum and zirconium. So here you are using this previous one you are using vanadium. So here you use a zirconium. Okay, it increases the mechanical strength even at high temperatures. Okay, and of course high loadability even in multi-axial stress states. This multi-axial stress states I will be explaining it when I am explaining about the anisotropic property of the 3D printed materials. Okay, and also it will having good buildability. So if you are uh, creating a part using this material, okay, it can be weldable. Okay, so weldable is nothing but you will be introducing into a large temperatures. So even at high temperatures, it has to have good properties. That is why here the first material characteristic is. Okay. So for this reason, they are used for engine constructions. Mostly they are using for engine constructions. Then titanium grade 2. Okay, this is an commercially pure available pure titanium grade with good, excellent biocompatibility and mechanical properties. Okay, since it is having good, excellent biocompatibility. Okay, so it is used for mainly used for medical applications. Right. Next is cobalt based alloy. So this is again a cobalt, chromium, and molybdenum. Okay, so this is a combination of this, and it is having exceptional biocompatibility. Okay, so since it is having excellent biocompatibility used for medical applications. Okay, and for implants and process works. And next another is a trademark material of this SLM company, that is Medident. So this dent you can see it is mainly used for dental purposes. Okay, so that is for teeth. Okay, so you can also create or 3D printed teeth which is teeth which is particular for a machine Okay, right. This is about your cobalt based alloys. Next is iron based alloys. Okay, so in iron based alloys, obviously stainless steel powders. Okay, stainless steel powders are used wherein this obviously why you are using stainless steel, because it is having a good corrosion resistance. Okay, so because all the utensils which are used in our kitchens are having good corrosion resistance. We need to be corrosion, because if you are using chloride means nothing but the water is having high content of salt. Only if you are using a stainless steel, it won't get reacted. Okay, so that is stainless steel. So similarly, if that is the requirement for an industrial application wherein you are going for a very salty environment, a working environment, so you'll be going for stainless steel powders. Okay, it has a very good corrosion resistance, high strength under elevated temperatures. Of course, since you are when you are cooking, you'll be using a temperature more than 100 degrees Celsius, nearly 100 to 150 degrees Celsius. Yes, so it has to withstand that temperature also. So these materials make them application good for aerospace, surgical instruments. Of course, surgical instruments, that is the knife and the punctures which are used in your operating surgical operations. You will be going for only stainless steel. Okay, that is iron based, rely on stainless steel powders. Then is maraging tool steel. This is 1.270 is the marketing name given by this company, but it is colloquially called as maraging tool steel. Okay, maraging steel. Okay, which is have a high content of nickel and molybdenum. Okay, so this steel will be having combination of iron, nickel and molybdenum. Okay, so it is having a very good Martensnake hardening. Martensnake hardening is nothing but one of the uh, crystal structure that has been obtained when you are heating the steel. Okay, it will be having a very high toughness and very high tensile strength. So usually this tensile strength and toughness are inversely proportional. Okay, when you are increasing tensile strength, the toughness will decrease. Okay, so it will having good properties of up to 400 degree Celsius. Application here is nothing but injection molding, which is one of the primary applications of this material. Next is one of the again a trademark material, that is iron FeAlloy Inver. Okay, so it is having a nickel containing in the steel that has a very low coefficient of thermal expansion below its Curie temperature of 20 degrees Celsius. So it will be having very low coefficient of thermal expansion. It means it has a higher dimensional stability at wide range of temperature applications. Okay, so dimensional stability is nothing but, so you know already, when you're increasing the temperature, the material or the component will try to expand. Okay, usually when you're decreasing temperature, the material will try to contract. So this is how your nature's law works. Okay, so when you're increasing the temperature, even if it is withstanding the temperature, it should not change the dimension. For example, if I'm having a length of about 100 centimeter length is I'm having for a particular component, if you're increasing temperature, that 100 centimeter should not change. It should not expand. Okay, so that is how this particular material is finding its application. Okay, so this material characteristics will help you at aerospace applications, because in aerospace applications you are using it in a higher altitude where the temperature is low, but the having both the temperature, on the outside the temperature will be low and the inside the temperature will be high for the aircraft engines. Okay, of course in valves and engines, on all the engines and precision instruments. Okay, so these are your iron based alloys. Next is copper based alloys. Okay, so this is copper, nickel and silicon chromium thing. So since your this copper will be having good conductivity, but this copper doesn't have other properties like corrosion resistance. So this will be increased through your nickel and silicon. Okay. So at higher temperatures, copper, since it is copper is having a good electrical conductivity, it is used in higher temperatures. But at higher temperatures, the copper will be losing stiffness. Okay. So that is why if you are adding the nickel and nickel, silicon, chromium into it, it will be adding the other properties which copper does not have. So due to low additives, the properties of pure copper can be considerably improved, while the other properties, large like electrical conductivity, are maintained. They are also retained. Okay, so it has a balanced combination of electrical and thermal conductivity. So this will be having both the electrical and thermal conductivity, and also high wear resistance. So since this is having a good these metal properties, finding its application in building technology. Okay, then is bronze, copper, tin, that is tin. Tin is, you will be calling it as stannum tin. So this is a copper tin alloy. Okay, this copper tin alloy is nothing but a bronze. Okay, it has a good wear properties and resistant to atmospheric corrosion and cavitation in sea waters. So if you are want to create a material which is used for shipping industries, you will be going for this particular type of materials. Okay, maritime applications. So these are your quick glance through of your materials, that is aluminum based alloys, okay, the nickel based alloys, titanium based alloys, cobalt based alloys, iron based alloys, and copper based alloys. So these are the current materials that is trending in the selective laser melting applications. Okay. Next is binder jetting. So you obviously know what is binder. I hope everyone are remembering it. So binder jetting is where you will be having the material is in the powder form, and you will be dropping the binders in the liquid form like this. So you will be having powder materials, okay, and you will be going for the binder or the solvent which is dropped from the nozzle. So only the areas the powder materials which is getting in contact with the binders or solvent will get reacted, and they'll be joining together or bonding together. Okay. So this is one of the technology which I have already seen. So this is an ideal binder, because when you are talking about binder jetting process, okay. So the powders which are being used in the SLS and SLM can also be used here, okay. But the main difference is the binder which is you are using, okay. So usually the binders will be of two types, which we'll be discussing it now. Okay, so a binder, an ideal binder would have a low viscosity, which allows the stream of individual droplets beads to form and then break from of the nozzle rapidly. So your binder must be having control over the application like this. Okay, you should not flow easily. You should be able to control it. Only then you can deposit the binders on the required areas of the powder. Okay, and one more thing is it should have the capacity or the very low viscosity in order to form the droplets. So this you can have a combination of water and an oil. Okay, so if you are dropping the water and oil, you can see water will be dropping by drop. It will be falling down drop by drop. Okay, but when you are using the oil, you can see a stream of oil that is getting down. It won't form droplet easily, the oils. Reason is the water is having a very low viscosity and the oil is having a very high viscosity. Okay, so for this binders you need very low viscosity like water. Okay, that only then there are two advantages of having low viscosity for binders. One is it can form droplets and it be easy to control. Second is it can easily penetrate into the gaps between the powder particles. Okay, so that is why you need a low viscosity binder. Okay, binder must be of low viscosity and must have stability against the large shear stress induced by printing. So because when you are printing, you'll be moving the nozzle at forth and back. Okay. So during that, the shear stresses will be induced during the on the binders liquids. Okay. So it should withstand it, and good powder interaction. Powder interaction, it has to interact and penetrate into the gap between the powders. Clean burnout characteristics, because we already know you'll be performing post processing for the binder jet produced products. Okay, I hope everyone knows this. One is sintering and another one is infiltration. Okay, so during sintering, we will be exposing it to high temperatures in order to remove the unwanted or excess binders. Okay, so it has to have clean bond characteristics, long shelf life, and acceptable environmental risk. Okay, so mostly binders will be of polymers. Okay, so there is an question for whether it is eco-friendly or not. So mostly the organic binders are recommended so that they'll be having biocompatibility. Okay. So this binding technique is having of two types. One is in liquid binding and in bed binding. Okay. So when you're talking about this in liquid binding, the binding agent is entirely carried by the jetting liquid. So the liquid which is coming from this nozzle will itself having the binding agent. Okay, that is in liquid binding. So it will be getting dropped on the powder particles and it will be bonding it. Okay. Next, second category is in bed binding. Okay, so in bed binding is this liquid will be, there's a simple rheological liquid. Rheological liquid is in order to increase the fluidity, you'll be introducing some other liquids and interacts with the dry glue particles embedded in the powder bed. So powder, when I'm talking about powder bed, this is the powder bed. Okay, the powder bed is nothing but already you are placing the powders on the build platform. That is the powder bed. Okay, so this powders will be having the glue particles. Okay, so these liquid particles will be trying to be a solvent. So I don't know when you know about the many of you have heard about the glue called as araldite. So araldite will be having two tubes. That is industrial glue. One tube, if you're using the two tubes separately, the it won't bind. Okay, so you need an initiator to start the binding process. So that like that will be using the embedding binding. So there will be one component that will be mixed with the powder particles here, and the second initiator will be dropped by this nozzle. So these both gets interacted, and they'll be trying to bond the interparticles of your powder bed. Okay, so these in liquid solutions they'll be having cross-linking agents like butyryl resins, polyvinyls, polysiloxanes, and polyacrylic acids. Okay, and in bed mechanisms they'll be having a starch, dextrostin, maltodextrin, and silica colloids. Okay, so usually if you're using in-bed mechanism, they'll be having very much higher voids because it won't have proper penetration. But if you're going for in liquid solutions, it has a good drying things, but they have an premature failure because preheat due to drying of glue agent in the nozzles itself. Nozzle itself, due to the heat, the glues will get blocking the nozzle tubes. Okay. Sometimes you can also use photocurable binders as well. Okay. So this is about a binder jetting processes wherein these are the binders, and these are the binding materials used for binding jetting applications. So this is we have already discussed it when we are discussing about the binder jet process. Okay. So this is about your laminate object manufacturing materials, which is also usually in a solid form. Solid is here as sheets or rolls. So these I have already discussed for in your previous when I explained this SLM technology. That is craft paper, butcher paper, standard copy paper, okay, sheet metal, ceramic filled tapes, polymers. Okay, so these are the variety of materials used for laminate object manufacturing, which is in the solid form. All right. So this is for today. If you got any doubts, please let me know.